If you look at a healthy Azure Service Bus architecture, you should see a zero count in the dead letter queue. But there is a widespread misconception that the DLQ is simply a waiting room for messages that fail processing. The DLQ is a graveyard. It is a diagnostic tool intended exclusively for messages where further retries are pointless. A common anti-pattern occurs when engineers let exceptions bubble up naturally through their code. A transient network error happens, the code throws, and the message eventually falls into the DLQ by default. This passive approach compromises system stability. Message settlement is an active, defensive engineering responsibility. You have to tell the broker exactly what to do with a payload when things go wrong. Treating the DLQ as a passive catch-all turns a temporary back-end blip into a permanent queue incident. Messages that should have been processed smoothly after a brief delay are instead buried, requiring manual intervention to recover. To see how this happens, let's trace a standard consumption flow. An order-created message arrives in the main queue, and a consumer picks it up to update a target database. Azure Service Bus then uses plock, temporarily locking the message and hiding it from other consumer instances while this specific node processes it. But then an infrastructural outage hits. The target orders database suddenly goes completely offline. The consumer cannot process the payload. The consumer node now holds a locked message it cannot process, and it faces a critical engineering choice regarding how to settle it back to the broker. Making the wrong settlement choice at this exact moment triggers a cascading system failure. There are 4 ways to settle a peak-locked message. First is complete, which signals the broker that the work was successful, and the message is permanently destroyed. Second is abandon. This immediately releases the lock on the broker, placing the message right back in the queue so a consumer can grab it again. Third is lock expire. If a consumer crashes mid-process and fails to respond, the broker's timeout threshold is eventually reached, naturally releasing the lock, just like an abandonment. And fourth is explicit dead letter, which instantly rejects the message into the DLQ, ensuring it will never be retried. The trap lies in the abandon mechanism. Every time a message is abandoned, the broker increments a hidden metric on the payload called delivery count. By default, Azure Service Bus enforces a strict max delivery count limit of 10 attempts. Consider what happens if that target database remains offline for a full 5-minute window. If your code catches the database exception and immediately calls abandon, the message goes straight back to the queue, gets picked up instantly, fails instantly, and is abandoned again. You have engineered a destructive hot retry loop. Because there is no delay between these attempts, the consumer burns through all 10 allowed retries in a matter of milliseconds. The immediate outcome is that a perfectly healthy payload is forcibly dead-lettered by the broker with a max delivery count exceeded error, long before the database ever has a chance to recover. Immediate abandonment is a strategy strictly reserved for microsecond network blips. It is incapable of handling actual infrastructural outages. Relying on default retry counts during an outage thrashes your backend resources and buries healthy data. The architectural alternative to the abandon loop is catching the outage exception and deliberately scheduling a delayed retry. You achieve this by leveraging a property called scheduled enqueue time. Instead of abandoning the current message, your consumer constructs an entirely new, forward-looking retry message and dictates exactly when the broker should make it visible. To prevent your system from hammering a struggling database, you apply exponential backoff and jitter to these scheduled times, spacing out the recovery attempts. This new message requires strict metadata tracking. You must append custom properties, specifically the current retry attempt count, the original operation ID, and the failure category. Then comes the critical, counterintuitive step. Because you have safely scheduled the retry, the consumer must explicitly complete the original locked message to destroy it and prevent native broker retries. The primary benefit here is complete isolation. The scheduled retry remains invisible on the broker, completely out of the consumer's way until its specific time delay expires. In practice, this maps to a safe timeline. A failure occurs, a 30-second retry is scheduled. If that fails, the consumer completes it and schedules a 2-minute retry, giving the infrastructure actual time to heal. Maintaining the original business operation ID inside the custom metadata ensures perfect traceability across these separate message instances. You must allow the broker to generate a new, unique message ID for this scheduled retry. If you copy the old ID, Azure's native duplicate detection assumes it is a redundant send and drops your retry. Scheduled backoff protects the database by strictly controlling the pace of retries, keeping the DLQ entirely isolated for true failures. To use the dead letter queue correctly, you must draw a strict boundary between an environmental outage, like a database drop, and a permanent poison message failure. Poison payloads are structural errors. This includes malformed JSON arrays, payloads using unsupported contract versions, or messages missing required primary keys. The golden rule for poison payloads is simple. 1,000,000 retries will not fix a syntax error. Never retry them. When your code catches a parsing or validation exception, it must explicitly dead letter the message instantly, appending a clear dead letter reason to the metadata. You should also add a custom application metadata tag to these payloads, such as retryable equals false. By isolating poison payloads this way, the DLQ becomes a highly specific diagnostic tool meant exclusively for bad data, not a catch-all bin for transient system issues. Eventually, an incident will exhaust even your scheduled backoff budgets, leaving healthy but unprocessed messages trapped in the DLQ graveyard. Because we categorized our failures, triage is straightforward. We query the metadata, separating the payloads tagged retryable equals true from those tagged retryable equals false. The poison payloads require manual developer investigation and downstream code fixes. Automated recovery will not work here. Safely recovering the true exhausted messages requires building a dedicated, independent replay worker service. This worker reads from the DLQ, creates a fresh, identical copy of the payload, resets the retry trackers, and sends it back to the main queue. You must throttle this replay worker. Dumping thousands of messages instantly back into the main pipeline will immediately overwhelm a newly recovered, fragile database, causing a secondary outage. Recovery must always be a controlled, deliberate injection back into the ecosystem, and never a blind dump of the DLQ. In distributed queues, network blips, scheduled delays, and manual replays mean the system will eventually process the same message twice. To survive this reality, you need one non-negotiable architectural requirement: idempotency. By checking a stable operation ID against the database state before executing a write, you ensure a business action is only executed once, regardless of how many delivery attempts the broker makes. Without idempotency, robust queue retries will blindly execute duplicate operations, which silently corrupts your critical financial data and system state. To build a resilient messaging architecture, use ordinary broker redelivery mechanisms strictly for microblips. Use scheduled, delayed retries for controlled backoff during infrastructure outages, and reserve the dead letter queue solely for permanent structural failures and exhausted backoff budgets. A truly reliable Azure Service Bus design dictates exactly when and why messages return to the processing cycle.